Today we want to introduce some concepts that we're going to need for the next video, where we're going to introduce a thermal climate model. So the first thing we want to talk about is heat transfer. For our purposes, the most important means of heat transfer will be radiation. But I would like to mention convection and conduction briefly. Conduction is all about the vibrational energy of molecules. So if I take my warm hand and place it on a cold desk, then the molecules in my hand are vibrating around. And when I place my hand on the cold desk, they're going to shake the molecules that are in the desk and transfer some energy to the desk. Of course, the desk is going to warm up a bit. So that's conduction. Convection is all about the flow of molecules because of variances in the density of a liquid or a gas. So we can imagine the air molecules above this flame here are going to spread out as it heats up, and that's going to create a region where we have lower density. And up above here, the cooler air is going to have a higher density. So we got a low density down below and a high density up above, and the higher density stuff is going to fall down, lower density stuff is going to go up, and we're going to get what are called convection currents. So in this case, the heat is transferred by means of convection currents. And the third type is radiation. And the reason that climate model, we're of course going to be concerned about the sun. All the energy that's really coming to the earth is coming from the sun. For practical purposes, there's no molecules. It's essentially a vacuum between the earth and the sun. So convection and conduction can't take place. All the energy that's reaching us from the sun is via electromagnetic radiation. The electromagnetic radiation that we usually associate with heat is in the infrared region of the spectrum. So you often hear of things like infrared heaters and that type of thing. Now, the total power radiated from the sun is 3.8 times 10 to the 26 watts. That's 3.8 times 10 to the 26 joules of energy are being radiated every second from the sun. Now, of course, it's a very small fraction of that total that actually hits the earth. We can imagine drawing a circle around the sun. The sun's at the center, and the earth is right on the periphery of that circle. And it's actually going to be a big sphere. It's going to be a three-dimensional circle. And all the radiation, there's going to be a very small fraction that hits the earth. And what we're going to try to do is calculate the intensity that strikes the earth. So we're going to kind of imagine that we hold up a 1 meter squared, say, piece of cardboard at the surface of the earth and ask ourselves how much power will hit that 1 meter squared piece of cardboard. That'll be called the intensity. And we're going to need to know the radius of this sphere, the distance from the earth to the sun, and that turns out to be 1.5 times 10 to the 11th meters. So basically what's happening there is all that power gets spread out over a very, very large area. And of course the area of this sphere is 4 pi r squared, the surface area of any sphere. So that energy is going to get spread out over that area. This power per meter squared, that's called the intensity. And for the earth, it'll equal the power divided by the area. And our area, of course, is this 4 pi r squared, where r is the distance from the earth to the sun. If you work that out, you get this value of about 1,340 watts per meter squared. If I hold up that piece of cardboard 1 meter squared, it would be receiving 1,340 watts. But we'd actually have to do that at the top of the atmosphere and not at the surface of the earth. It's going to be a little lower when you're at the surface of the earth. It's also going to be generally a little lower than that because the path that the Earth takes around the sun is not a circle, so that value of r isn't a constant. And so it actually ranges, just due to that elliptical nature, because the distance is changing, between about 1,000 and 1,400 watts per meter squared. Okay, and this is still at the top of the atmosphere, but the atmosphere blocks out about 30% of the energy. And what that means is that on a really cloudy day, hold up your piece of cardboard right at the surface of the earth, you're only going to get about 2 watts per meter squared. And on a sunny day, it'd be up to about 1,000 watts per meter squared. Okay, so more energy is blocked by the atmosphere. And in fact, if we consider an average value where we're considering day and night, clear and cloudy, etc. And the average value striking our piece of cardboard right at the surface of the Earth would be 170 watts per meter squared. Okay, read over this question, try it on your own, and then come back for the answer. So we're looking for how much solar radiation, the amount of energy that would strike our 1 square meter of cardboard at the Earth's surface over a full day. So an easy way of doing this one is to take that average value of the intensity at the Earth's surface, which is 170 watts per meter squared. I'm going to convert that to kilowatts, so that's 0.17. I'm just dividing by 1,000 kilowatts per meter squared. And then if I multiply that by 24 hours, I'll get hours times kilowatts, which is kilowatt hours. That's a unit of energy. That comes out to be 4.1 kilowatt hours per meter squared that would strike in one day. Now, you're probably familiar with things that glow and take on a characteristic color. We could talk about things that are red hot or white hot, and something that's white hot is actually hotter than something that's red hot. The color that something glows with when it's really hot is an indication of its temperature. And this glow that things take on when they're hot, that's blackbody radiation. So we want to talk a little more about this blackbody radiation. We'll start off with what's called a blackbody radiation curve. So we can imagine we take one of these glowing objects. Let's say it's at 3,000 degrees, and we measure the intensity of the radiation coming off the object at different wavelengths. So across here we've got increasing wavelength, and there'd be some wavelength, looks like right around here at 1 micrometer, where you're getting a peak lambda. That would be lambda peak. If we go up to a higher temperature, lambda peak is in the visible region of the spectrum. And if we go up to an even higher temperature, 12,000 K, then our lambda peak is actually in the ultraviolet region of the spectrum. And that's why we get different glow colors as we change temperature, because that peak intensity is changing as well. And also notice that as you get hotter, you're getting a lot more radiation being given off because there's a lot more area under the curve. Now, if we look for a pattern between these peak wavelengths, I kind of see that they're kind of curving here. Turns out there is a relationship between the temperature of the black body and the peak wavelength, and it's given by this Wein Displacement Law, which says that the temperature in Kelvin will be equal to a constant that's around 2.9 times 10 to the minus 3, that's meters Kelvin, divided by that peak wavelength. So for instance, if the peak wavelength is 483 nanometers, I would divide by 483 times 10 to the minus 9 meters. Of course, the meters will cancel out, and I'll get a temperature in Kelvin. And if you do the math, it turns out that's 6,000 K. So if somehow we're able to analyze the light coming off a black body, a glowing object, and we find that peak wavelength, we should be able to estimate what the temperature of the object is. So why do we have this name black body? Well, if we had, say, a piece of paper, it looks white because light is coming and reflecting off it. But if we have something that's glowing, then the light is just kind of radiating outwards. And so we can have two objects that are white, but for very different reasons. One because of reflection, one because of radiation being emitted from the object itself. A black body is an object that only absorbs radiation. It doesn't reflect radiation. So any color that a black body takes on would have to be solely due to that glow, that emitted radiation, and it would not at all be due to reflection. So a black body, it's just to make you think of a body that's going to absorb all the radiation that's incident on it. Now, not all materials are just as good as other materials at radiating heat and glowing. And so we have to introduce this concept of emissivity. And emissivity just basically tells you how good of a black body a material is. And it's going to be a number always between 0 and 1, so it's just a fraction. It would be 0 if it's a perfect reflector. And if it's a perfect absorber, a perfect black body, then the emissivity would be 1. The emissivity is simply equal to the power that would be radiated by a perfect black body at a given temperature compared to the power radiated by the specific material that you're talking about. So when we have shiny objects, they're going to have low emissivity. They're good reflectors. If we have black objects, then we're going to get emissivities near 1. Black materials tend to absorb radiation very well. Now, if we look at the whole Earth atmosphere system, of course, the atmosphere is always changing. Sometimes we have lots of clouds, sometimes not so many clouds. But generally, the emissivity as a whole of the Earth atmosphere system is about 0.64. We have something called the Stefan-Boltzman Law, which says that the total power radiated by a body varies as the 4th power of the temperature in Kelvin. And for the case of really an ideal black body here, then we can write it this way. We can put an equal sign and use this constant here, which is called the Stefan-Boltzman constant. And it's in your data booklet. It's equal to 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4th. And we've also got to multiply by the area, the surface area of our object. Most of the objects we're talking about will be spherical or nearly spherical, so that means that our area would be 4 pi r squared. Typically, we write our Stefan-Boltzman law in terms of intensity rather than power, and so that would mean that the intensity would be equal to that expression that we just wrote down, sigma A t to the 4th. But for intensity, of course, we divide the area out, so we're just going to get an expression with a sigma and a t to the 4th. And remember, the SI units for intensity, that's power or watts per meter squared. Power striking per unit area. We can start applying this Stefan-Boltzman law to any material if we bring in the idea of the emissivity. So this is just going to be a fraction between 0 and 1 that'll give us the correct amount of power coming out of any body. It doesn't have to be an ideal black body. And if you look at the emissivity of most of the things on the surface of the Earth, it's all quite high. It's all fairly close to 1, all over 0.9, except maybe some brands of soil. And I would imagine that this 0.75 value would be some sort of white sand that would reflect light quite well. A concept that's very closely related to emissivity is albedo. And albedo is just the fraction of the incident radiation that's reflected from a surface. So anytime we have some light coming in on or electromagnetic radiation coming onto a surface, some of it gets absorbed and some of it gets reflected. And we're just looking at what fraction gets reflected. Now, of course, all the radiation that comes in has to be either reflected or absorbed, and that means if we know the albedo, we also know the fraction that's absorbed. So, for instance, the albedo of the Earth, so the L of the albedo of the Earth is on the average equal to 0.3, and that would mean that 70% or 0.7 of the light, 70% of the light is absorbed. And notice here, this chart's kind of interesting. This is, here we're just looking at different types of clouds, and notice here that the emissivity of clouds is relatively low compared to surface elements like snow and soil, etc. And that the albedo is above average. The albedo of the Earth atmosphere system is about 0.3 as a whole. It's 0.39 for the clouds, at least the upper clouds. The surface clouds tend to have a very high emissivity, and a low albedo. So we've got all kinds of different surface coverings on the Earth, quite a range of albedos. It turns out the average albedo of the Earth is about 30%, or 0.3 as a fraction. So an important question that we can ask ourselves is what effect will melting the glaciers have on the Earth's overall temperature? If we imagine the glaciers would be here as ice, and let's say that underneath the glaciers is some sort of wet sand, then of course we're going to move towards a lower albedo if the glaciers melt. And if we're moving to a lower albedo, that means there's going to be more absorption. And if there's more absorption, that means there's going to be more radiation emitted. And that's going to raise temperatures. So actually having a high albedo reduces the temperatures of the Earth. Okay, a quick question. I'd like you to read it over and try it out, and then come back for the answer. Okay, so in this question, the original albedo, we've got to imagine that's going to be halfway between 0.2 and 0.4 because we've got 50% water and 50% ice. So originally, alpha is equal to 0.3, halfway between 0.2 and 0.4. Now afterwards, I'll call that alpha primed, we're going to have 60% water, which would mean we've got to weight this 0.2 higher than we weight this 0.4, because there's only 40% at 0.4. If we do that, we should get a value here of 0.28. So you notice that the albedo changes by 0.02, and it's lowering. So that melting will lower the albedo by 0.02. We have one last concept to introduce. That's the surface heat capacity. Of course, it's going to be very connected to the regular specific heat capacity. The difference being that it's going to be the amount of energy required to raise a unit area, usually of the surface of the Earth, by 1 degree Celsius. The two, of course, will be connected. This mass here, mass is equal to density times volume, and volume is equal to area times depth, at least using a simple model where we have a equal depth all the way through, which means that we can write the specific heat capacity here as C equals Q all over rho A times depth. And now if I multiply both sides by rho and depth, what I'm going to get here is that rho times the depth times the regular specific heat capacity will be equal to Q all over A delta T, which is just the surface heat capacity. So if I take my regular specific heat capacity, multiply it by the density and the depth, I'll get the surface heat capacity. Let's try one question involving the surface heat capacity. Read over the question, try it yourself, and then come back for the answer. Okay, so hopefully what you did, you maybe started with the definition of the surface heat capacity equal to Q all over A delta T, and the heat that's being added should equal the power times the time. And you'll notice here that P over A, that's just the intensity, so we've really got intensity times time over delta T must equal this surface heat capacity. And we know the surface heat capacity, we also know the intensity, so we know that I, and we also know the delta T. That means we're going to be able to solve for the amount of time it's going to take. That will be equal to CS delta T all over I. Let's put the numerical values in. It's 4.2 times 10 to the 8th. That's joules, meters to the minus 2, Kelvin to the minus 1. Change in temperature was 2.0 degrees Kelvin, and the intensity was the 340 watts times meters to the minus 2. Just checking in on the units here. Those are going to cancel out. The kelvins here will cancel out. That leaves you with joules over watts, which is joules over joules per second, which is just seconds, which is what you're expecting. And it should come out to be 2.5 times 10 to the 6 seconds. If we convert that to days, we get 29 days. That answer assumes that you're always getting that same intensity of radiation on the lake all the time. Of course, that's not going to be happening at night. So in fact, the time's going to be considerably greater than 29 days. Okay, so let's try to briefly summarize all the concepts that we've learned in the video. The first thing that we talked about was the three forms of heat transfer, which included conduction, which was really about molecular vibration, convection, which was about molecular flow, and then radiation, which was really electromagnetic radiation. Then we introduced the solar constant, which was about 1340 watts per meter squared, and that would be the amount of energy striking per square meter at the top of the atmosphere. We talked about how an object might appear a certain color because of light reflecting off it, but that objects could also glow and give color that way. And that led to these blackbody radiation curves, which for a higher temperature would have a sharper peak and look something like that. Lower temperature, it looks something like that. Each of these would have a peak wavelength, and on this side of the axis was the intensity. So we were looking at how intense was each wavelength. This led to the Wein Displacement Law, which allowed you to calculate the temperature if you knew the peak wavelength of the radiation, of the emitted radiation. And then we talked about the Stefan-Boltzman law that said that the power being emitted from any black body varied as the fourth power of the temperature in Kelvin. And then we wrote this as an equality, introducing the Stefan-Boltzman constant, the area, which would generally be 4 pi r squared times t to the fourth. This led to the concept of emissivity, this fraction that varied between 0 and 1, 1 for a perfect black body and 0 for a perfect reflector. And this emissivity was telling you how good of a black body is it. It's just a fraction. It compared the power emitted from a particular material to the power emitted by a perfect black body at the same temperature. And then we introduced albedo. It was just the fraction of radiation reflected from a material. And then the last idea that we talked about was the surface heat capacity. So if we're talking about heating up the Earth, we're more interested in how much energy it takes to raise a given amount of surface area by 1 degree Celsius. And that would be your surface heat capacity. And that's all for today, folks. Thank you very much.